Okay, thank you very much for attending my talk. So I prepared some statistics for Mark, just it's more private. So I prepared in the morning, because I have bad memory, so I may give some wrong numbers. Yeah, so before I start this mentioning a bit the private stuff, I want to mention the mass biology group at Alberta started a long time ago, like 1980s. So at that moment, we have seen some names like Butler or Gail Orquist or those Herb Friedman or some names in some talks. So that's like long tradition from 1980s. Yeah. And then Mark jumped in about around early like 2000, right? Early 2000, yeah. So it really expanded this reputation and the group after 20 years. So he just led our group like in the past 20 years. Yeah. So we really enjoyed it. And Mark, of course, inspired a lot of our research, mainly research of my lab. I think that's the main point, including some people here, like Chris Heglut or Yuri Selmani or Jude Kong or Jingjing Xu here. Yeah, so inspired a lot of new ideas or research in my lab. Yeah. So of course, also including other colleagues, yeah, in mass bio and also dynamic systems. That's when I talk to dynamic system people, they are motivated by applied problems from you. And some of them directly work with you as well. Yeah. So he has been very influential in our group for that past 20 years. And of course, we expect him to be part of our team as Elementar's professor in future. So in the next 10 years, still will be part of our team and continue inspiring our research. Yeah. And a bit of statistic about, I'm just curious, I also don't know. So I checked this morning about our joint stuff. Like we published 15 joint papers together. It's a big number, but it's over 14 years. So I count, it's one paper a year. So it's regular. So I expect maybe continue similar tradition in future, a paper a year. And of course, several in progress. So maybe around 4 or 5 in progress. And the topics is very wide, actually, very wide. So that's surprising to me. So each topic, we already collaborate for one paper almost. So I think it's very wide areas, like toxic contaminants and methane production emission from oil sands industry. So it's more like industrial pollution. So that's one big area. And species invasion, I think both Mark and I have some common interest on species invasion. And algal bloom predictions. So we also have a couple of papers on that. And recently, COVID-19 forecasting or prediction using whatever machine learning or integration of machine learning and dynamic systems. Yeah, and also some like early warning signals, also relevant to the machine learning and also maybe a bit bifurcation theory coupled together. And of course, animal movement. So the interesting thing is animal movement, we just chatted very recently. We have, I think that's maybe main research interest of Mark's team. But for me, I'm kind of new. So I just maybe joined this effort maybe 5, 6 years ago, something like that, yeah. And I learned by myself first and also my team. Yes, I merged to, I just try to approach Mark's study. Then maybe after 3 or 4 years, then I tried to approach him. Then we chatted maybe during the COVID period. So we have regular meetings in discussing that cognitive animal movement with memory, how we model those things. Of course, we didn't resolve those things. We just chat for ideas, you know, maybe not lead to papers, but I think I learned a lot from that process, yeah, including Peter Thompson here. Yeah, so we have regular meetings on that during the COVID period. Yeah. And approaches, yeah, I may take a bit more time. So approaches including something like non-smooth dynamical systems. It's including stoichiometry. Also for those toxic models, we have some non-smooth features. And difference equations for invasive species and transient dynamics. That's we have a lot of interest on transient dynamics. And recently machine learning plus dynamical systems. And I think we are still in kind of the way of exploration. So we expect to have some novel ideas or output from the coupling of machine learning and dynamic systems because of lack of prediction power from deterministic model, even stochastic model. So that's like drawback or something about mechanistic models. Yeah. So maybe coupling can help us. Of course, there are drawbacks of machine learning. The machine learning have a lot of requirements on the good massive data. So if you have bad data, if you don't have enough data, it's a problem. Cannot tell you underlying mechanisms, give you prediction, but don't know what's going on. So maybe coupling can give us some interesting ideas. Yeah. And we co-supervised 4 postdocs before, and 2 graduate students before, and 1 undergraduate student. Yeah, so that's the history. And now we are co-supervising 1 postdoc and a couple of graduate students still. So I think we'll continue this tradition. Yeah. And for grants, we had 6 joint research grants and 3 joint event grants. Yeah. So I was surprised when I saw these numbers. I never counted. Yeah. So I think it's massive numbers over like past 14 years. Yeah. So I really appreciate Mark's support and inspiration to my team. Yeah. Okay, so this one I just had the job to determine topic. Because I just said a lot, right? Very broad spectrum of areas. So I picked this one. Few reasons. This one is more abstract, so I think it's easier to finish within 15 or 20 minutes, because I expect I only have 15 or 20 minutes to finish this one. So if larger project, then it's harder. So this one more like abstract framework, so it's more conceptual than the real, just real applications. Yeah, but we expect maybe we can modify this for real applications. Yeah, so you'll see some abstract ideas in this so-called free boundary or the moving boundary for habitat. Yeah, so sorry, can I show this? Oh yeah, so these 3 words, you will see that soon. Okay. So this is joint work with Mark and a colleague at HIT, Chun Chen, and a joint PhD student, Chun Xi. So he is at Alberta now. Yeah, so I will show something maybe in addition, also motivated by Mark at the end, and it's also new to Mark. Mark never saw that. So in the end of we'll show something new result beyond whatever published. Yeah. So we start from this very well-known free boundary in physics. So that's called the Stephan condition for just ice melting, right, at the interface of water and ice. Yeah. So I don't have time to go through details or derivation, but you can see something new here, right? Simple PDE. Then we have something new here, S of t, right? So this one is a variable, right? So the boundary is a variable. And S prime depends on this, proportional to this gradient. So U sub x. And this gradient for this right side boundary, it's always negative. So this one always positive. So this makes this pretty simple story. Just S keep increasing, almost the case, right? So which means the habitat just keep expanding as long as the species persists, right? So that's the case. Of course, that's a big question mark because that's for ice melting. In ice melting, no problem because just keep melting, nothing else, right? But when I apply this to biology, of course, we have a big question mark. Why always like that? So I think I use what Thomas told me, just no biology in this one. It's just physical condition. Yeah, it's a physical condition, a physical setup. Yeah. And this one actually, this simple form already applied in many places, in college or in this physiology or tumor growth. Of course, Thomas doesn't like that, of course, because it's stable condition or some modified version of that, but still keep the feature of that stable condition, and which makes probably little sense can be in biology, right? So that's a question mark. Yeah. Of course, that doesn't mean we can reach the correct version of that, but we just have this question mark in mind and hope we can have one step ahead beyond this physical free boundary, right? So it just borrowed from physics. Right? Okay, obviously it will be more challenging, right, for analysis or for simulations. Yeah, but for stable condition analysis is okay, not that hard. Because if we introduce a transformation, then I can mention it here. So that's the model, right? So if you analyze this one, what you do is just introduce a transformation. Then free boundary will be fixed boundary. Of course, the formation PD will be a bit more complicated. So something will be getting to there. But still, those comparison principle, upper lower solution constructions, those still work. So it's not that big a deal, actually. That's why mathematicians like that, because it makes model more complicated, but the effort in math is not that hard, just a little bit of effort. So it's okay, right? So that's why mathematicians do like this. So this is one example from Du and Lin. They studied this, just use Stephan condition. So coupled with some kind of visual KPP, or whatever, simple form, right? Simple form PDE there. So what they can show is mathematically, just two cases. Even they don't prove this, we can imagine this. Just keep expanding, right? One case, as long as we have persistence. So if population goes to some equilibrium, it's positive, then you have persistence, then the boundary just keep expanding forever. Of course, probably not that reasonable, but that's the ice melting case. And the other case, if you want to stop expanding, it's possible. The species cannot survive. So if species go extinct, then that gradient term will tend to zero as well. So you just stop expansion, right? So that's the case they showed. So that's rigorous result mathematically. And one interesting observation from the mathematical study is, suppose we have spreading, okay, then the speed of moving front is constant, it's proved rigorously, which is less than well-known minimum traveling wave speed, right, to square root of AD. So it's slower, kind of slower, right? And many people extended this to double free boundary. It's not hard. You just have to copy paste the other side, right, more or less. But it will be opposite sign because this G will keep decreasing. Because for G equation here, this gradient will be positive. So that makes it negative. So the other side will keep decreasing. So both sides will have expansion. Yeah. So another question mark is, of course, quantitatively they are different if you compare traveling wave or the free boundary, but the qualitatively no big difference because it seems like we have it's not really that free because they just keep expanding and depend on any biology kind of. That's the feeling, right? Because you just give that condition, a stable condition, and keep expansion, right? So no biology getting into that. Then I just from imagination I thought, oh, maybe not always they expand the habitat. So I just have this picture in my mind. It's not done yet, this one, just for motivation. Yeah. So the model here will be much simpler than this one. So if you have this snowshoe here and the lynx, of course, that's popular in Alberta. We have a lot of snowshoe hare lynx. Even in my backyard, I see one lynx and a lot of snowshoe hares. So if these snowshoe hares just have their den or their home in the middle, for example, then if you use the free boundary to say they claim that these lynx just keep expansion, it's not reasonable. They just go away, right, from what they need. So it's not reasonable. Yeah. So modeling this one is in progress. So I just recently asked a new PhD student, Yulei, actually come from University of Miami, transferred from there as a new PhD student to work on this problem. So of course, this one we can see this to determine the free boundary, it will depend on these guys. So these guys' interaction, so it's more like, should be something like perception or cognitive modeling, more or less. Because if they know the information, then they will judge whether they should expand or not. So the free boundary should depend on those things. Of course, that situation will be much more complicated in the modeling. So it's relevant to my talk given in CMS meeting, cognitive animal movement modeling, like how they get information and keep in memory, then to make a decision. So it's also relevant to that. Yeah. And the version I show here, it's phenomenological, very simple, right? Very simple. But I think it's one step ahead of that physical condition. Okay, physical ice melting condition. Okay. So for this phenomenological modeling, we just have some assumptions or conceptual ideas. So the rate of boundary shift is determined by weighted population inside the range. So it's kind of a collective decision depending on those individuals, kind of, right? So, and we give some kind of weight. If far away from boundary, less weight, closer, it's higher weight. And the weighted kernel includes repulsion over short spatial scales and aggregation over long spatial scales. That's not hard to understand. If we just get too close, then too crowded, so we lack of resource. It's kind of too dense, right? Too dense. It's not good. So if it's far away, it's better, right? So that's kind of the idea for creating this weighted function. Yeah. So we can see this one looks more complicated compared to the stable condition. So h prime equals mu times this non-local term. So we have seen some non-local form, but still same as the stable condition because you can extend the stable condition to the non-local form. So then the results no difference. But this one will be different because of the kernel here. It doesn't follow that stable condition. So the kernel has two pieces, this exponential function minus this one, and these conditions C1 greater than C2, both positive, and alpha 1 greater than alpha 2, both positive, will give crossing. So it's possible you have like expansion or shrinking or even equilibrium, because the stable condition has no equilibrium, no steady state. Okay, so we can see sign switch, right? So in the next slide, we can see, we just judge the sign for this. J is this integral, right? The whole integral, give a new name. And individuals benefit from longer range interactions with other individuals, but suffer if they are too close, right? It's too dense. So that's kind of mechanism to drive this model here. So if we look at this J, we can plot it, this kernel, right? This weighted, so-called weighted function, W1 minus W2. So they cross, and we can see there's a threshold, right? H tilde, less than that, W less than 0, and greater than that, W greater than 0. And how to determine this J is positive or negative? We just count the area, right? So this area should be the negative area between green and the red curves. This area should be positive area. So we just add up. If positive, it's positive. If negative, it's J is negative. That will determine expansion or shrinking. Right? Yeah, so it's very conceptual. It's very conceptual, this development. Yeah, so interesting thing is we can show the stable condition is a spatial limiting case. So it's spatial and also take a limit, so we can get that. Yeah, so it's good Mark called that. So Mark wrote this derivation to connect the classical version and our version. Yeah, so it's better to sell the model. It's relevant to that physical condition. Although that's not right, but sometimes that's right. So that's not always wrong, right, the stable condition. Yeah. Okay, so the new model is like this. If we pile them together, right, so given some mild conditions, so it's pretty standard classical. Some mild conditions, we can show the local existence and uniqueness of solutions. Of course, no biological insights, just guarantee model works. Model makes sense, right? Because when we have introduced some new model with the integral, it's possible. It's ill-posed. It's not it's a problem that doesn't work, right? Even mathematically. And we show the global existence of the solution. Okay. And long-term behavior, that's a big assumption. Yeah, I think Xiaoqian just talked to me about that. That's a big problem because stable condition, the limit always exists. But here, it's a big question. So if anyone can prove this, that's a big gain, I think, to push the model. So if we assume the limit exists, then we can show this dichotomy. This one similar to the Stefan one. So it's kind of mimic that one, no new insights here. Right? So still like either extinction or expansion, right? Those two cases. So what's new here? Here we have a steady state case. So we can get some kind of internal positive steady state, right? And that will drive some interesting dynamics, of course, for this one. And of course, equilibrium satisfies these conditions. So this one more complicated because you see it's H star, U stars everywhere, not just in PDE. Because if in PDE, it's much easier, right? So it's more complicated than that. So this proof of this theorem. So I think this one, we have very, very strong condition. So we are not happy with that very strong condition. But at least we want to get this right. So Mark and I really spent maybe a couple of months, I think, keep discussing how to make this proof correct. So logically, we understand what's going on. But when you write down the proofs, always, if you check second time, third time, some problem. Yeah, so if it's not rigorous, that's fine. You know, that's logically we know how to get this one. But when we write down, always a problem. So eventually, we have to make a very strong condition here. So this theorem is weak, but to guarantee it's correct. Okay, guarantee it's correct. We have it's kind of existence of steady state. And that's a very important point from this model. And of course, we have this trichotomy now, right? Vanishing, balancing, or spreading, right? Spreading. So it's more complicated and more reasonable, we think. So some simulations. Yeah, I think I will have 3 minutes. Okay, some simulations. So these just key parameters. I don't explain these parameters, just key parameters in that weighted function, right? So if you change these parameters, we can see different cases. So you can see shrinking of this habitat, right? So shrinking, and this kind of new phenomenon. And this first case is extinction. Second case, persistence. So this is equilibrium case, shrinking to equilibrium. This one also equilibrium, but it's expansion. So expansion to equilibrium, or we just keep expanding. So this one is similar to the stable condition. So stable condition can be right in some cases, but not always. And we can also check the spreading speed versus these parameters in that kernel or weighted function. So it's always monotone, so either increasing or decreasing. And we can also check this impact of the initial position of the free boundary. That will determine the fate of the species. So either extinction here or survival and expansion. So this kind of, we have the conjecture, we cannot prove this, but there's a conjecture, there's some threshold H hat to give this dichotomy. So similar conjecture for the initial condition. So if we choose different initial conditions, we can also have different cases. And we are specifically interested in this, how this free boundary or moving boundary, depending on these different initial positions and also the intrinsic growth rate. So we can see different cases. If H no is small, right, initial position of the free boundary is small, then we can see just either increasing or just constant, right, just constant, stays there forever. Or the other two cases, if initial position is large, then we have increasing, stabilized, or decreasing, so all possibilities. Right? So we have this conjecture also cannot prove this. It's not easy to prove. So this H bar, there's a threshold to give this dichotomy here. So if H no greater than H bar, then see it's kind of will be less, limit will be less than H no. And the other way will be greater than H no. And the double front spreading, we can just metric way, right? Make that. And I don't put the theorem here, but it's similar. And we can have some interesting simulations. So this is a symmetric case because we choose the symmetric parameters in both weighted functions. So it's a symmetric case. So this one in parallel to that one-sided free boundary, right? Or we can have a symmetric case. So this is interesting. We can see that if C1 is small, then we have kind of a shrinking of the habitat and shift to the right, and extinction of the species. And or the other case, just no expansion or shrinking, just stay the same, the habitat size, and it's more like it looks like a traveling wave or like climate-driven shifting, more like that, but it's from free boundary. So the habitat just shift to one direction, right, with the same size. And can be expansion, right? Can be expansion and move to the same side or different side, like different directions, right? Different directions. So symmetric case. Of course, that's not explosive. Maybe we have more cases. Right? These are just examples. And the challenge here, mathematical challenge, of course, because the sign of H prime is not necessarily positive. So we need expert mathematician like Xiaoqiang to help. Xiaoqiang said he has extended this to some other things to do rigorous analysis. So this one, of course, big question mark here. Big question mark here. And because existing methods don't work, that's also that state case very challenging. That's all available techniques. We tried. I think Mark suggests almost all possibilities one by one. Yeah. So just tried, then work. Tried, then work. Yeah. Okay. So maybe I take 1 minute in the end. It's draw by hand. Sorry. So and it's hidden because not published and even not close to get it done. I just want to show you some exciting stuff. Also motivated by Mark for that finger-shaped. That free boundary. So the reason we do this is because of that motivation. So it's kind of a rectangle case, but one side is free boundary, any shape, it can be any shape. And the model is hidden, and we can show, of course, the existing uniqueness, those basic theorems, long-term behavior. And we want to show this, and the state, okay, satisfied, also hidden, okay. Because if this is given, the model is given, yeah. And this one is the state case. So in the transition, of course, you'll see something like this. So in the transition, it will be more irregular. Even this picture is not stabilized, still in transition. Yeah. So, but this gives the possibility, you have the finger shape, and finally maybe go to some more regular pattern in the end. Yeah. And unfortunately, this one mathematically it's almost hopeless. Okay, this model hopeless, and also numerically also hopeless. So we tried all methods. So for example, we have seen like non-local case for the free boundary, like Abner Friedman, they also did that. But their case we checked, it's very spatial. So very, very symmetric, and cannot give random shape, they cannot give that. So it's still reduced to one-dimensional simulation. So it's not included there. Yeah. So we are still working on that too. That's why I don't show the transition. That's harder. For equilibrium case, we have the program, we can do it. But for the real, with time evolution, it's challenging. Mathematically, I think hopeless, but numerically, hopefully we can develop something in the near future. Yeah, that's why I don't show Mark anything because still in progress. Yeah, yeah. So we have Yeah, so this one motivated by this Sam Levin's paper and his collaborators. Yeah, some people from Sam Levin's group here. Yeah, so that's we start from that shape because of this motivation. Yeah, and we really try to explain this without assuming sine function or cosine function. That's not fun. That's if you just give that, it's not fun. So we hope we can get from real free boundary with any shape, and finally we get some pattern relevant to that. Yeah, so that's our imagination and still progress. Okay, so maybe I skip this. So there are a lot of interesting problems to keep going, especially the last one. We are in progress, and it's, of course, even in modeling, we need to debate a lot. Yeah. How to connect from that motivating picture. Yeah. So how we do that. Yeah. So I think Yulei is working on this, but I haven't really involved in this progress. And finally, most important thing, happy birthday, Mark. It's his very important 60th birthday. And thank you very much for all your support. And this is a picture, I think, taken before COVID. So about 18, so maybe you see a lot of familiar people here. Right? So it's a bit dark, but it's, I think, in a park in Edmonton. So we have a summer school, I remember, right? We have a summer school, so I had this picture. So you see these two big guys lying down on the floor. Okay, thank you very much.